Bismillahirrahmanirrahim. Assalamu alaikum. This is my second video on math education, math teaching, and the topic today for lecture is differentiation. I will be talking about differentiation, what a derivative is, how it comes into being, and what is its physical interpretation. Because we will be taking start from some other things and eventually we will get to the derivative. So you will know about the physical interpretation without me telling you. Anyhow, it's like I'll be telling the physical interpretation or physical significance of differentiation before defining it. And in the end, we'll be practicing a few examples on differentiation. So let's get started. I am going to start with another thing, which is not exactly derivative. Let me take some coordinate axes. This is some coordinate system. Let's say an xy coordinate system, x-axis and y-axis, and I assume a curve on this coordinate system. Now if I have two distinct points P and Q on this curve, then the line joining these 2 points is known as the secant line. What is that called? That is called secant line. You may see that if I move this point Q towards point P along the curve, then the secant line is rotating, isn't it? See, if my point Q comes here, secant line becomes like this. If my point Q comes here, secant line is like this, and so on, right? So in this case, when I haven't rotated the point Q, when my point Q and point P are where they are, let me assume that the coordinates of point P are x0 and y0, and that of point Q are x1, y1. Then if I write about their slope, then the slope of this secant line is f of x1 minus f of x0. Value of the function at this point minus value of the function at initial point divided by final point minus initial point, that is x1 minus x0. You may already know about the definition of slope, which is m equals y by x. Simply we just say that. Actually this is y equals mx plus c. Here we are not going to talk about this. Maybe we consider this later, but for the time being we are just not going to discuss this. So that was it. When my points were where they were, we just simply wrote it like this. Simply the formula for slope, f of x1 minus f of x0 divided by x1 minus x0. Now let's suppose the limiting condition. See, this is my coordinate system and I am drawing the same curve. I'm just taking now those points where my points P and Q are located, only that part of the slope. Okay, you can increase it if you wish. So where this projection of point P meets x-axis, this is x0, and where it meets the y-axis, this is f of x0, and where this point P joins point Q, that line is known as the secant line. And where this point Q, this projection meets point x-axis, this is x1, and where this joins the y-axis, that is f of x1, and horizontal to the x-axis. So this much portion is f of x1 minus f of x0. right? And this much portion from this to this, or you can say from here to here, this is x1 minus x0, right? So now I'll be talking about the limiting condition when my x1 is approaching x0. You can see when I say I am trying to move my point Q towards point P, it seems like I am trying to move my x1 towards x0. So let's assume that my point Q reaches point P. What will be the secant line then? If my point Q is lying exactly above point P, what will be my secant line? This is no more a secant line, it becomes a tangent. So at this point, when my x1 approaches x0, the secant line becomes a tangent line. This is a tangent line, and this is the theta. As you can see, initially the secant line was making this much theta, and when it became tangent, the theta, the angle was changed. This is the other angle. Is that clear? Now if I'm trying to write about the slope of this tangent line, okay, let me make a little changes. I might not write it only m, let me write it m tan, so that we can find the difference between the two, and let me write this one as m secant. Okay, so m tangent, I can write it as f of x1 minus f of x0 divided by x1 minus x0. Then what's the difference between the two? There is one main difference, and that is the limit. Tangent is actually the limiting case of a secant when x1 approaches x0. So this was basically the definition of a tangent line. What exactly a tangent is? Usually we are taught in small classes in junior levels that a tangent is defined as a straight line which touches an arc or a circle at one and only one point externally. This is not the exact definition. The exact definition is that tangent is the limiting case of a secant line, right? So now we talk about average and instantaneous velocity. What is average velocity? It is more generally defined as the total distance traveled divided by the total time elapsed. Suppose a car travels 75 miles on a straight road in a 3 hours period, then we can say that the average velocity of the car is 25 miles per hour. Obviously, if an object travels with an average velocity of 25 miles per hour during a 3-hour trip, it need not travel at a fixed velocity of 25 miles per hour. Sometimes it may speed up and sometimes it may slow down. Now, although average velocity is useful for some purposes, it is not always significant in physical problems. For example, if a moving car strikes a tree, the damage is not determined by the average velocity, rather it is determined by the instantaneous velocity at the precise moment of the impact. Like you can say, for example, if a car was moving and it came in contact with a tree and the accident happened, so we are not going to see what the average velocity of the car was. Like for example, it started from 0 and then it was it sped up to 20, then it rose to 50. Sometimes there was traffic signals or there were road bumps or other things. It slowed down. It had approximately 0 speed at 20 or 30 again. But at the time of the impact, when it was hitting the tree, what exactly was its speed by that time? So in these instances, we are more interested in the instantaneous speed and not in the average speed, right? So our goal is to define the concept of instantaneous velocity in a way that it can be calculated and worked with mathematically. For this purpose, consider a car that moves in a single direction along a, like you can see in this diagram, along the straight road on which a coordinate line has been introduced with its positive direction in the direction of the motion of the car. As shown in the figure, if the clock tracks the elapsed time starting with t equals 0 to some other time t, then after t seconds the car will have some coordinate s, that is a function of time. Like I can say s is a function of time, s equals f of t. The graph of this function in a TS coordinate system is called the position versus time curve for the motion. Like you can see here, this is the TS coordinate system and this is the curve. This is the curve which shows the motion of this car. And the position versus time curve provides a simple geometric interpretation of the average velocity of the car over a time interval, say from t0 to t1. We'll be drawing another thing in order to understand it fully. So if the car has a coordinate, let's say s0, let me draw this again. Let me have another coordinate system, a TS coordinate system, time and s, which is the distance. So let me draw it here. Let me say that this is the curve for the motion of the car. So this is the curve which shows the motion of the car, and let me say that the coordinate of the car, that is s0, which is equal to the function of t0 at instant t0. Let me call this t0. So the coordinate was s0 at time t0 and another coordinate be s1 at time t1. Let's suppose this is another coordinate which is a function of t1 and at time t1. So and here we have to remember that our t1 is greater than t0, right? Then the distance traveled during the time interval is s1 minus s0. This is the distance traveled in this time interval. Which time interval? The time interval is t1 minus t0, right? So this is the distance traveled and this is the time interval. Then what will be the average velocity during this time interval? So the average velocity will be equal to V average is equal to, because we said average velocity, like we said it above, is equal to distance traveled divided by time elapsed. So distance traveled here is s1 minus s0 and the time elapsed is t1 minus t0. We said s1 was the function of time at the interval t1, so I can write it as f of t1 minus, instead of s0 I can write it as f of t0 divided by t1 minus t0. Now you can see that this is precisely the slope of the secant line joining the 2 points, joining the 2 coordinates s0 to s1. You see, this is what the average velocity is actually the limit, the slope of the secant line, because this is the average, so it is equal to slope of the secant line. I can say that V average is actually equal to slope of the secant line. Now let's talk about the instantaneous velocity. In order to find the instantaneous velocity, we will let our t1 get closer and closer to t0. Then our average velocity in the interval from t0 to t1 will get closer and closer to the instantaneous velocity at the time t0. Thus, if we denote the instantaneous by this is going to be equal to limit t1 approaches t0 f, sorry not f, this is s, s1 minus s0 divided by t1 minus T naught. Limit T1 approaches T naught. S1 can be written as a function of T1 minus function of T naught divided by T1 minus T naught. Because when we were approaching, the T1 was trying to approach T naught, this point S1 was coming closer and closer to S0. The secant line turned to a tangent line. So instantaneous is equal to the slope of the tangent line. This is actually equal to slope of the tangent line, which we already found, and that was equal to limit T1 approaches T naught, and the same things again. So we can say that V instantaneous is equal to the slope of the tangent line. It's like we said, V average was equal to the slope of the secant line, so instantaneous is equal to slope of the tangent line.